Welcome to the Deep Dives. We're here to explore some really critical research, helping you understand the big forces shaping our planet. And today we're looking at something huge, essential, but maybe a bit unseen, a global climate system facing, well, a really profound challenge. We're talking about the Atlantic Meridional Overturning Circulation, AMOC for short. Just picture this giant conveyor belt in the ocean, okay? It's constantly moving heat, carbon, nutrients all around the globe. It's absolutely fundamental. But here's the kicker. This massive system, it seems to be weakening. It may be faster than we thought. Now, when something that crucial is in trouble, scientists obviously start looking at interventions, things like Stratospheric Aerosol Injection, or SAI. The idea of cooling the planet to maybe help systems like the AMOC. But here's the puzzle, and it's a big one. Past research on whether SAI could actually save the AMOC has been, well, all over the place. Contradictory, even. It's left researchers sort of scratching their heads. So, yeah, what is going on there? Why the disagreement?
That is exactly the mystery. And some new research just out in 2025 from Bednar's and colleagues is starting to shed some real light on this. They use these incredibly detailed simulations with the community or system model, specifically the latest version, CESM2 WACCM6. For those maybe not familiar, this is like one of the most advanced climate models we have. Simulates everything, deep ocean, high atmosphere, the works. And their findings. They offer this really critical insight. It seems the key isn't just if we inject aerosols. It's much more specific. It's where we inject them, the latitude. That might be the deciding factor.
Okay, the where. That makes things interesting. And that's really our mission for you today. By the end of this deep dive, you should have a much clearer picture of the AMOC, why its decline is, frankly, scary. And crucially, how the precise location of something like SAI could mean restoring this ocean current, or having almost no effect at all. It really feels like a potential game changer. Okay, so let's back up a bit. Can you maybe simplify the AMOC for us? What exactly is this ocean's beating heart doing?
Absolutely. So think of it like a huge continuous loop, right? In the Atlantic, it starts near the tropics.
Yeah.
You have warmer, pretty salty surface water flowing northwards. As it gets way up north into the colder subpolar Atlantic, it gives off heat to the air, cools down, and gets denser. Much denser. And because it's denser, it sinks, like thousands of meters down into the deep ocean. Then, this cold, dense water flows south again, deep underwater, eventually cycling back up, completing the loop. And this whole thing is just fundamental. It's like a global thermostat moving enormous amounts of heat from the equator towards the poles. It helps regulate temperatures everywhere. It moves carbon around, cycles nutrients. I mean, marine life depends on it.
A global thermostat. That's a really powerful image. But, and this is where it gets pretty concerning. This isn't just theory. The AMOC is changing right now, alarmingly so. Projections show it weakening further as the planet warms. And some research suggests it could hit a, well, critical tipping point, maybe as early as the mid-century. Studies from Ditlevson and Ditlevson Van Westen et al., well, they really highlight how close that might be. And it's not just future worries. We know from other work, Caesar et al., for instance, that the AMOC is already weaker now than it has been for over 1,000 years, a millennium. That's staggering.
It truly is staggering. And the consequences of a major slowdown, or God forbid, a halt, they're dire. And global. We'd be looking at really drastic shifts in temperature patterns, rainfall patterns, think droughts, floods in new places, major changes in sea ice, potentially significant sea level rise, especially hitting the North American coast hard. And then you've got the knock-on effects. Agriculture disrupted, ecosystems both in the ocean and on land thrown completely out of whack, food security, biodiversity, it's all connected. When you start listing the impacts, you realize just how much relies on this one current.
So what does this all mean for you listening right now? It means this deep ocean current humming away silently has consequences that ripple right across the planet. It affects your weather, maybe even the food available to you. It's this quiet workhorse, and if it seriously falters, well, we're all in for a very rough ride. Okay, so faced with that grim picture, where do scientists even begin to look for solutions? One idea that keeps coming up, though it's highly debated, is Stratospheric Aerosol Injection, SAI. Can you just quickly outline what SAI actually involves?
Sure. So SAI is basically a proposed climate intervention technique. The idea is to mimic the cooling effect we see naturally after huge volcanic eruptions. You'd inject tiny particles, usually sulfate aerosols, or the chemicals that form them way up into the lower stratosphere. Once they're up there, these aerosols reflect a bit of sunlight back to space before it reaches the surface. And that reduces the overall energy coming in, which should cool the planet's surface temperature, hopefully offsetting some effects of greenhouse gases. Okay, now here's where that puzzle, that disagreement, really comes into focus. When scientists started modeling SAI running simulations, they got these really different answers about what it would do to the AMC. bafflingly different. For example, there was a big project called GLNS. They used an earlier climate model, CESM1, WACCM5, their results. They suggested SAI could lead to substantial AMC strengthening, a big boost. But then another major effort, ARISE SAI 1.5, using the newer model, CESM2. Their simulations showed SAI doing almost nothing for the AMC, just a slight reduction in the rate of decline. So you had these two cutting-edge projects, and their results were just miles apart on this really critical question.
Wow, yeah, strengthening versus barely slowing the decline. That's a massive discrepancy, isn't it? And what was the initial thinking? Why such different outcomes? Because didn't both projects use fairly similar injection strategies, like around the tropics and subtropics?
That's exactly right. They both targeted similar latitudes, mostly. Location didn't immediately jump out as the reason, which led a lot of people to assume, well, it must be down to the models themselves, model-dependent representation of physical processes. Basically, the idea was that subtle differences in how each model calculated the physics must be causing the different AMOC responses. The where wasn't seen as the main driver.
Until this new study by Bednarz et al., right? That's one that flips the script, as you said.
Precisely. Their work really zeroed in on this. They found it wasn't primarily about the model differences, but critically about the latitude where the aerosols were injected. That's what seemed to control the AMOC response.
Okay, so how did they figure that out? What was their method?
It was quite clever. They ran what are called idealized simulations. They injected a fixed amount of SO2, that's sulfur dioxide, the precursor for the aerosols. It was 12 million tons per year, injected consistently between 2035 and 2069, at a standard altitude about 21.5 kilometers up. But the key was they systematically varied only the injection latitude. They ran separate simulations, injecting at 45 south, 30 south, 15 south, the equator, 15 north, 30 north, and 45 north. This setup allowed them to really isolate the effect of the injection location.
Very neat. And the results, you said, were starkly different depending on the hemisphere. What did they find for northern versus southern injections?
The difference was night and day, really. When they injected anywhere in the northern hemisphere, 15 north, 30 north, or 45 north, they saw a substantial AMOC recovery. It actually brought the AMOC strength back up to roughly where it was around 2020 by the year 2070 in the simulations. Injecting right at the equator seemed to stabilize the AMOC, basically stopping it from declining further. But, and this is the crucial part, injections anywhere in the southern hemisphere, whether 15, 30, or 45 south, they had little impact on the AMOC strength. They slowed the decline just a tiny bit, but that was it, even though those southern hemisphere injections did still cause significant global cooling overall.
Wow. Okay, let me make sure I'm getting this. You can still cool the whole planet with southern hemisphere injections, but if your goal is also to help the AMOC, injecting south of the equator just doesn't really do the job.
That seems to be the clear message from these simulations, yes. A really critical distinction.
And you also mentioned something fascinating, that all the northern hemisphere injections, 15, 30, or 45 north, they all produced roughly similar levels of AMOC recovery. How can that be? Surely injecting at different northern latitudes would create different patterns of aerosols, different amounts of cooling in different places up there, different AODs, as you call them.
That is a fantastic question, and it points to something really subtle. You're right, those different NH injection latitudes did produce significantly different patterns of aerosol optical depth, especially in the northern hemisphere extratropics, yet the AMOC recovery was similar. So what does that tell us? It suggests it's not just about the total amount of aerosol dimming over the northern hemisphere. It's likely more about how that dimming influences specific processes in the key region for AMOC formation in the North Atlantic. It seems you just need to trigger the right kind of change in that critical area.
Ah, okay. So it's not general cooling, but maybe triggering a specific effect in the North Atlantic, which leads us right to the next question. How? How do these northern hemisphere injections actually help the AMOC? What's the mechanism, especially at the start?
Right, the mechanism. So the first, say, 10 to 15 years of the simulations, the main driver appears to be changes in the surface heat flux over the North Atlantic. Basically, the NH injections cause the ocean surface in that region to lose more heat, either directly to the now slightly cooler atmosphere above it or to growing sea ice. So the surface heat flux becomes more negative, more heat is leaving the ocean. This cools the surface waters, which makes them denser. And as we established, denser water sinks more readily, which is what drives and strengthens the AMOC circulation.
Okay, that makes intuitive sense. Cooler surface, denser water, stronger sinking, stronger AMOC.
Right.
But what about salt? Salinity, doesn't that also play a huge role in water density?
It absolutely does. Salinity is incredibly important for the overall AMOC structure and density. But interestingly, in these simulations, during those initial 10-15 years of SAI, the surface salinity in the key North Atlantic regions didn't change very much. It showed very little change. So while crucial overall, salinity doesn't seem to be the initial trigger for the AMOC strengthening caused by NHSAI. Heat flux changes come first. However, and this is important, after that initial period, you start seeing these longer-term feedbacks involving salinity kick in. As the AMOC starts to strengthen because of the initial cooling, that stronger current begins pulling more salty water northward from the tropics. Plus, if there's initially more sea ice forming, the salt left behind when water freezes also increases surface salinity. These are what the paper calls AMOC adjustments. They then help to maintain and maybe even further enhance that stronger circulation over the longer run.
Got it. So it's like a 1-2 punch. First, the direct cooling effect boosts the sinking. Then, the stronger circulation itself brings in more salt, creating a positive feedback that helps keep it strong. Can we dig a bit deeper into those initial heat flux changes? What exactly is causing the ocean to lose more heat under NHSAI?
Sure. There are a few key components to the surface heat budget that change. First is the sensible heat flux. That's the direct transfer of heat from the warmer ocean to the cooler air. Under NHSAI, the ocean loses more heat this way. Pretty straightforward. Then you have the net downward shortwave flux, basically, sunlight reaching the surface. Initially, as you'd expect with aerosols reflecting sunlight, this decreases. Less sun gets through. But here's a fascinating twist. After about 10 or 15 years, the models show this trend actually reversing. The shortwave flux starts to increase again.
Wait, increase even with the aerosol still there. How does that work?
Yeah, it seems counterintuitive, right? The study suggests this is largely due to a reduction in low-level cloud cover over the North Atlantic in response to the SAI and the changing circulation. Fewer low clouds mean more sunlight can actually reach the ocean's surface, even with the stratospheric aerosols overhead. And the third key player is sea ice. Initially, the cooling from NHSAI encourages more sea ice growth. When water freezes, it releases heat, effectively meaning more heat loss from the ocean perspective. But then later on, as the AMOC strengthens and starts bringing warmer water northward again, the sea ice extent in the North Atlantic actually starts to decrease. Another complex feedback.
Wow. Okay, so it really is a complex dance. Direct cooling, changes in clouds, allowing more sun later,
Yeah.
shifting sea ice, all interacting over time. It's definitely not just a simple case of reflect sunlight, ocean cools, AMOC recovers.
Not at all. It's this interplay of the direct aerosol forcing and then these evolving, sometimes surprising feedbacks within the ocean atmosphere ice system.
Okay, so bringing this all together, let's go back to that initial puzzle. Those contradictory results from the earlier GLANS and ARISE-SciA 1.5 projects. How does this new understanding about latitude finally resolve that discrepancy? Does it explain why they got such different results?
It seems to, yes. The study argues quite convincingly that this newly revealed latitude dependence is sufficient to explain the difference. Remember, the GLS project, the one that showed stronger AMC recovery, it turns out their injection strategy effectively put more SO2, or its effects, into the Northern Hemisphere stratosphere, whereas ARISE-SciA 1.5, which showed very little AMOC benefit, their strategy injected most of the SO2 much further south, mainly at 15 degrees south. So based on these new findings, you'd expect GLNS to show more AMAS recovery and ARISE to show less, simply based on where they put the aerosols. It wasn't necessarily just the different model versions causing the disagreement, it was fundamentally driven by the aerosol distribution.
That really ties it all together. It clarifies a major point of confusion in the field. It wasn't just models being different, it was about where the intervention was happening. Okay, so let's try to recap the core message from this deep dive. It seems the location, the latitude of stratospheric aerosol injection is incredibly important, maybe even the most critical factor if the goal includes trying to stabilize or restore the AMOC. And we've seen just how complex these Earth systems are. You get initial responses, but then these longer-term feedbacks involving heat, salt, clouds, ice, they can really change the picture over time.
Exactly, and it's really crucial to reiterate that these were idealized simulations. Their purpose was to understand the mechanisms, the underlying physics and chemistry. They weren't designed as direct blueprints for policy. The study itself is very careful to point out that injecting aerosols only in one hemisphere, like the North, could have serious unwanted side effects elsewhere. They mention potential impacts on rainfall in places like the Sahel, for example. So these single hemisphere injections aren't being proposed as realistic strategies on their own. The real value here is highlighting how vital it is to understand these detailed processes, not just chase a simple global average temperature target. The regional effects matter immensely.
That's a very important clarification. Science illuminating the process, not necessarily prescribing the solution just yet. And that actually leads me to a final, maybe provocative thought for you, our listeners, to mull over. Given what we've just heard, how different things happen on different timescales, the initial 10, 15 years versus longer-term feedbacks, and knowing that the ocean, especially, responds slowly and has this incredibly long memory, what does that imply about ever trying to stop or significantly change an SAI deployment once it's started? If those initial choices about where you inject and how much lock in these really long-term climate trajectories, how reversible is it? Could mid-course corrections become almost impossibly complex ethically and practically? It really underscores the immense gravity of contemplating such interventions, something this research brings into sharp focus. Well, thank you for joining us on another deep dive. We really hope this has given you a clearer insight into our vital ocean systems and the very intricate science surrounding potential climate interventions.